Welcome to AI Taperslock. Today we are looking at GPU offload in Rust. Portable, safe, and fast by Manuel Astrelwald and team from the University of Toronto and Lawrence Livermore National Lab. So this paper introduces a zero-overhead, multi-vendor GPU compilation framework built natively into the Rust compiler, Rust, RustX, and LLVM backends. It basically brings Rust's strict compile time memory safety, specifically its ownership model, and strip aliasing guarantees like no alias to massively parallel GPU environments. And it achieves this without, forcing developers into vendor-locked domain-specific languages and without having to escape to explicit, unsafe raw pointers. It currently targets NVIDIA and AMD hardware, handling safe memory movements natively.
Yeah, and to fully appreciate why this architectural shift is generating so much excitement for AI researchers and machine learning engineers, you really have to look at the massive technical debt sitting at the foundation of modern high-performance computing. Right now, the entire HPC ecosystem is effectively handcuffed to languages like C, C++, Cetera, and Fortran.
Right, because of the bare metal speeds.
Exactly. We use them because they offer bare metal execution speeds, but they are inherently memory unsafe. When an engineer sits down to write a custom kernel for an NVIDIA or AMD GPU using native APIs like CUD or HIP, they're walking a tightrope without a net.
Yeah, zero guardrails.
Zero. The compiler provides absolutely no guardrails. The entire cognitive burden of preventing memory corruption, avoiding race conditions across thousands of threads, and orchestrating complex host-to-device memory transfers, all of that rests squarely on the human writing the code.
And humans are notoriously bad at tracking thousands of concurrent memory states. One slightly miscalculated offset in a matrix multiplication kernel.
Yeah.
And you've just triggered undefined behavior, silently corrupting your training data.
Precisely.
Which is why the ML engineering community has been staring at Rust for years, hoping it could be the silver bullet. The whole point of Rust is this borrow checker enforcing memory safety and data race freedom at compile time. But wait, haven't we seen Rust on GPUs before?
We have, yeah, but the historical fragmentation has been a huge deterrent. The community has certainly tried to solve this, but every prior attempt demanded a significant structural compromise.
Like what?
Well, if you look at Rust Grupu, which compiles Rust to 6CIV, it was fundamentally architected around graphics workloads. Even though they've tried to pivot toward compute workloads, it still lacks support for general pointers.
Oh, wow. In the HPC world, where you are constantly passing pointers to massive, complex tensor structures, lacking general pointer support is just a complete non-starter.
Totally. Then you had frameworks like Rust CUDA, which technically allowed you to write Rust, but forced you to wrap almost the entire kernel in unsafe blocks.
Which completely defeats the purpose of choosing Rust over C++ in the first place.
Right, exactly. And even the more recent breakthroughs like CUDA Oxide, which introduced some incredible compile time safety mechanics, well, they are strictly vendor locked to NVIDIA. If your cluster runs on AMD hardware, you're just out of luck.
So that vendor lock-in is exactly what makes this University of Toronto and Lawrence Livermore paper such a breakthrough. They aren't bolting a secondary tool onto the language, right?
No, they've solved the portability and the safety problems simultaneously by building the offloading engine directly into the upstream Rust compiler itself.
That is wild. I want to dig into the architecture of how they actually pull that off, because a compiler managing CPU host code and GPU device code at the exact same time sounds like a total logistical nightmare.
It is a massive engineering challenge, yeah.
Is it sort of like trying to translate a book into two different languages simultaneously while you're still reading it? Instead of reading the code and spitting out one binary, the compiler has to actively separate the logic.
That's a great way to think about it. It's almost like a film production pipeline. Pass 1 is the casting director figuring out exactly who is in the scene.
Okay.
Pass 2 goes on location to shoot the GPU-specific footage. And Pass 3 is the editor in the cutting room splicing that GPU footage right into the main host CPU timeline.
That production pipeline analogy maps perfectly to how the authors integrated this into Cargo, Rust's package manager, using a new experimental -z offload flag. The pipeline explicitly operates in 3 separate phases, which they call a multi-pass compilation pipeline.
Exactly.
That casting director phase you mentioned is Pass 1, and it focuses entirely on host metadata. Specifically, it collects forced kernel monomorphization data.
Right, and let's break down monomorphization for the listener, because that's a pretty heavy compiler term. When you write a generic function in Rust, the compiler doesn't just compile it once.
Right.
If you use it with a 32-bit float and a 64-bit float, it stamps out a unique, concrete copy of that function for both types.
Which is precisely why pass 1 is critical.
Mhm.
If your CPU host code invokes a generic kernel, the device compiler in pass 2 needs to know exactly which concrete types to compile for.
You nailed it. Pass 1 scrapes the host code, logs those concrete types, and hands that data forward. Then Pass 2 takes over the location chute.
So it generates the device-specific LLVM bitcode for whatever GPU architecture you're targeting, whether that's an H100 or an MI250X.
Yep, and it packages all of that compiled bitcode into a discrete device image file called device.bin.
Which leads to pass 3, where the compiler lowers the Rust offload intrinsics into LLVM intermediate representation, essentially using OpenMP or LLVM target runtime calls to manage the execution. It takes that device.bin file and beds it straight into the final host CPU binary.
Exactly right.
But I have to challenge the premise of needing 3 separate passes here. Frameworks like CUDA Oxide manage to do this in a single-pass compilation pipeline. From a compiler engineering standpoint, multi-pass architectures introduce a ton of overhead and cross-pass communication complexity. Why go through the hassle of multiple passes? Why not just compile it all in one go?
It's a fair question, but the authors provide a very compelling rationale for avoiding a single pass, and it comes down to how Rust manages architecture-specific optimizations. Rust heavily utilizes CFG attributes, conditional compilation flags, and inline assembly to squeeze maximum performance out of compute-heavy crates.
Okay.
If you attempt a single pass, the compiler is forced to evaluate those conditional attributes before it logically separates the host code from the device code.
I see the collision there. If the host machine is an x86 CPU, the compiler might see a CFG flag enabling highly optimized AVX512 vector instructions specifically for the host.
Right, and if that single pass hasn't separated the streams yet, you risk bleeding those CPU-specific AVX512 instructions directly into the GPU-compatible LLVM intermediate representation.
Oh, wow.
And translating by 86 vector instructions into something an NVIDIA streaming multiprocessor can understand is computationally infeasible. By enforcing 3 separate front-end passes, the framework guarantees that the CPU and the GPU evaluate their target-specific semantics in complete isolation.
So the host binary gets its AVX512 instructions, the GPU binary gets its native accelerator instructions, and they never pollute each other's compilation space.
Exactly.
So if the compiler is isolating these environments that strictly, it raises a huge practical question for the developer. How does the compiler know which way data is moving? If I declare a massive tensor on my CPU, how do I safely get it to the GPU?
By leaning on the natural semantics of Rust's type system, the framework introduces a mechanism called type-driven offload lowering. In safe Rust, variables are immutable by default. You have to explicitly declare mutability.
Right.
The compiler uses that distinction as the ultimate signal for routing data. If you pass an immutable reference, an &t into the kernel, the compiler lowers that to a mapto directive. Because it mathematically guarantees the kernel cannot modify that data, it only copies the memory in one direction, from the host to the device.
And if I pass a mutable reference, an &t, it triggers a mapto from directive. The compiler recognizes the kernel intends to change the data, so it automatically sets up bidirectional synchronization.
Yes, copying it to the device before execution and syncing the modified data back to the host afterward. With a small exception for scalars up to 64-bit, which are just passed by value to avoid pointer indirection overhead entirely.
That makes a lot of sense.
So from there, the authors designed 3 different developer interfaces to interact with this system. Interface A is what they call compiler-managed kernels. It's the ultimate plug-and-play experience. You just wrap your function in an offload macro, and the compiler handles every single allocation and memory transfer dynamically based on those reference types we just discussed.
Which sounds incredibly convenient, but looking closely at the mechanics, I see a massive performance trap hiding in Interface A.
Oh, yeah.
Yeah, the compiler is automatically managing bidirectional syncs based on host-side uses. What happens if I try to print a variable on the host to debug a mutable variable right between 2 separate kernel launches? Doesn't the compiler implicitly force an expensive device-to-host sync just to print the text, and then another host-to-device sync immediately after for the next kernel?
It absolutely does. The authors acknowledge that Interface A is fantastic for rapid prototyping, but that implicit synchronization overhead can quickly destroy your execution times. In high-performance computing, accidental data movement is the enemy.
Right. Moving memory is always the bottleneck.
Precisely. This is why they offer Interface B and Interface C. Interface B is designed for interoperability with vendor libraries. Most AI infrastructure relies on highly tuned C++ math libraries like cuBLAS or RockBLS, which manage their own memory. Interface B allows developers to wrap those foreign function calls safely.
So integrating vendor kernels alongside custom Rust kernels within a unified memory model.
Exactly. But Interface C is where the pure Rust magic happens. This is the explicit type-staged memory control.
I love Interface C. I look at it like checking your code at a cloakroom. You hand your data over to the GPU, and the cloakroom attendant gives you a ticket in return, which in this framework is a preload or preload mutt struct.
That's a really good way to visualize it.
Right. And as long as you hold that ticket, you literally cannot access your code. The Rust compiler will throw an error if you try to read or write to the original host value. You only get access back when you hand the ticket in, which happens when the preload struct goes out of scope and is dropped.
The cloakroom analogy perfectly captures the ownership transfer. You are making the physical location of the data explicit through the Rust type system itself. To implement this ticket system without relying on standard Rust references, which would cause lifetime conflicts, they rely on raw host pointers under the hood, but they bind them to safe Rust lifetimes using ghost types, specifically phantom data.
So they're essentially tricking the borrow checker into enforcing GPU memory states.
Well, tricking is a strong word, but they are creatively leveraging it. A preload struct acts as a proxy for an immutable borrow, and a preload mutt acts as a proxy for a mutable borrow. The runtime uses reference counting to manage the allocations. Yeah, if you preload an immutable reference multiple times across different kernels, it just ticks up a counter. It only frees the device memory when that counter hits 0. Conversely, because a preload mutt represents a unique mutable borrow, the compiler knows it cannot alias.
Oh, I see.
So when that preload mutt ticket is dropped, it explicitly fires the device-to-host transfer. It completely neutralizes the println performance trap you noticed. If you try to print the data while the GPU holds the preload mutt ticket, the borrow checker just violently rejects the compile.
All of this brilliantly solves moving the data safely. But once the data is on the device, we run headfirst into the central tension of using Rust for parallel computing. Rust's foundational golden rule is aliasing XOR mutability.
Right, the core rule.
Yeah, you can either have one single mutable reference to a piece of data or multiple mutable references, but never both. So how on earth is it logically possible to run a parallel GPU kernel where thousands of concurrent threads are all mutating the exact same tensor simultaneously? By Rust's own rules, shouldn't that instantly trigger undefined behavior?
It is the ultimate paradox of GPU programming in Rust. If you give thousands of threads a mutable reference to the same array, the compiler will panic. To solve this, the authors engineered an abstraction called a region, which utilizes a partitioning strategy trait.
Okay, pure Rust implementations.
Yes. The framework doesn't give every thread access to the whole array. Instead, these pure Rust implementations mathematically carve the memory block into disjoint chunks.
Disjoint meaning the compiler can definitively prove that no two threads will ever attempt to access the same memory address.
Correct. The partitioning strategy calculates the indexing boundaries internally and then hands each individual thread a safe, mutable slice of only its assigned chunk. Because the compiler can verify that these slices never overlap, the borrow checker's requirement for unique mutability is perfectly satisfied. You get the ergonomics of safe Rust slices inside your kernel, while the front end secretly manages the raw pointer arithmetic required to distribute the workload.
That is an elegant workaround. But are there any exceptions where they have to use unsafe code? Like if I'm writing a complex matrix multiplication kernel, are there any edge cases where this disjoint chunk model falls apart and I have to escape back to unsafe raw pointers?
There is one critical exception where safety is suspended, and that's GPU shared memory. Shared memory is an ultra-fast, limited-capacity scratchpad that is private to a specific thread block.
Right.
Unlike global memory, where threads work in isolation, shared memory exists specifically so threads can actively cooperate, look at each other's data, and perform complex reductions. When you request shared memory using the framework's glupal launch-sized workgroup mem function, it does not return a safe reference. It returns a raw pointer.
Wait, really? Why give up the safety guarantees there? If they solved global memory partitioning, why can't they partition shared memory?
Because the very nature of shared memory violates the disjoint chunks requirement. The authors document 4 severe safety hazards that make wrapping shared memory in safe Rust nearly impossible.
Okay, what are they?
First, out-of-bounds accesses if the kernel exceeds the dynamically requested memory size. Second, offset calculation errors when packing multiple different structs into the same raw byte array. Third, alignment issues, where casting a generic byte pointer to a type with strict alignment requirements can cause a hardware fault.
Oh, sound nasty.
They are, but the fourth and most difficult hazard is concurrent mutation. Because threads use shared memory to exchange data, they are constantly reading and writing to the same addresses.
Oh, so if the compiler thought those were standard safe references, it would assume they don't alias and make aggressive optimization decisions that would literally corrupt the data at runtime.
Exactly. Building compiler-level proofs to mitigate all 4 hazards wasn't worth the overhead, so returning a raw pointer acts as a massive warning label for the developer.
That makes perfect sense, yeah. Sometimes exposing the danger is safer than poorly abstracting it. So let's look at the actual performance, because in HPC, if it's safe but slow, nobody will use it. We discussed that interface A has a performance trap regarding implicit synchronization. If a developer is prototyping and uses interface A inside a tight loop without thinking, isn't it going to bottleneck the GPU terribly?
Horribly. The author's baseline testing showed that a naive, unoptimized implementation of interface A ran over 400 times slower than a manually optimized version. The synchronization overhead was crushing.
Wow, 400 times. So how do they fix it?
To fix this without forcing developers to abandon the easy interface, they prototyped advanced compiler optimization passes directly into the LLVM OpenMP opt infrastructure.
What specific optimization passes did they build?
They focused on 2 techniques. First, automatic data prefetching. The compiler analyzes the execution graph, splits the memory transfers into separate asynchronous LLVM calls, and fires the host-to-device transfer as early as possible.
Yeah.
It only blocks the CPU right before the kernel absolutely needs the data.
Okay, making transfers async. And the second?
Second, they implemented a highly specialized variant of loop-invariant code motion, or LICM.
So they analyzed the LLVM intermediate representation to find redundant operations inside a loop and hoist them out.
Exactly. If the compiler sees a loop executing a kernel 100 times, but the underlying data being passed in doesn't change between iterations, it realizes that syncing the memory 100 times is useless.
Right.
The LICM pass physically moves the LLVM data transfer instructions out of the loop block entirely. It pushes the data to the GPU once before the loop starts and pulls the result back once after the loop finishes. Those automated passes made the plug-and-play interface A perform almost identically to the heavily manual interface C.
That is some serious compiler magic. But the ultimate test is the RAJAPerf benchmark suite. They evaluated this framework against highly tuned native C++ on serious enterprise hardware, an AMD MI250X, and an NVIDIA H100. When you strip away all the theory, what's the final verdict? How do the rest execution times actually compare?
The results validate the entire approach. On both the AMD and NVIDIA architectures, pure Rust kernel execution times were incredibly competitive, running essentially on par with the hand-optimized RAJA and RAJA HEPC++ baselines.
That's huge.
It is. There was a slight divergence on 2 specific micro-benchmarks, FIR and L times, where Rust was slightly slower.
Why did Rust struggle on those 2 specifically?
Basically because they are exceptionally tiny operations. In the FIR benchmark, each thread is just executing a tiny handful of multiply and add instructions. When a workload is that small, execution time becomes hypersensitive to how the compiler decides to unroll loops. The performance gap wasn't an inherent flaw in Rust. It was simply a difference in the loop unrolling heuristics between RustEDX and the C++ compiler.
I want to point out a really strange anomaly in the data transfer benchmarks on the NVIDIA H100, though. According to the paper, the Rust framework transferred less data overall, 423 megabytes, whereas the RAJA C++ baseline transferred 468 megabytes. But despite moving less data, the Rust transfers took 46 milliseconds, while the C++ transfers took only 16 milliseconds. How does a framework transfer less data but take almost 3 times as long to do it?
Yeah, that anomaly highlights the hidden complexities of asynchronous memory pipelines. The authors trace this back to the OpenMP offload runtime that Rust is utilizing. Even though it's moving fewer raw bytes, the underlying memory kinds being allocated and the way the asynchronous transfer pipes are structured in OpenMP aren't quite as streamlined as native CEDA's proprietary pipelines.
No, that makes sense.
They also observed that Rust's register usage on the GPU was slightly elevated, averaging 33 registers per kernel compared to 28 in C++ way.
Let me guess, that register bloat is the cost of Rust's safety checks.
Largely, yes. When you write standard Rust for a CPU, you use iterators, which inherently bypass bounds checking because the compiler knows the length. But inside a GPU kernel, you have to explicitly index into the arrays using thread and block IDs.
Right.
Because Rust refuses to compromise on safety, it injects bounds checking logic for every single array access to ensure a thread doesn't read out of bounds. Storing those boundary limits consumes a few extra registers. Although, to Rust's credit, the authors noted that this slight increase in register pressure didn't measurably degrade runtime performance on these specific benchmarks.
Let's address the final massive technical hurdle, which revolves around floating point math. In the C++ AI ecosystem, developers aggressively rely on a compiler flag called fastmath to squeeze out maximum teraflops. Fast math allows the compiler to make dangerous assumptions, like assuming a calculation will never result in not a number or an infinity value.
Yep, it's very common.
But if you make those assumptions in safe Rust and a NAND value actually occurs, you trigger undefined behavior. So Rust strictly forbids fast math. If you can't use fast math, how can Rust possibly compete in floating point heavy machine learning workloads?
By leaning on a brilliantly experimental feature in Rust called algebraic floating point operations. Algebraic floats offer a middle ground. They expose the vast majority of the aggressive instruction reordering and optimization opportunities that fast math provides, but they explicitly exclude the no nan and no infinity assumptions.
Oh, nice.
Yeah, this allows the compiler to aggressively optimize the math without ever risking memory safety or undefined behavior.
Did utilizing algebraic floats actually close the performance gap in the testing?
Spectacularly, when the authors tested the FIR kernel on an NVIDIA RTX A2000, swapping standard floats for algebraic floats doubled the execution speed.
Wait, really? A 2x speed up just from that?
Yes. Removing those strict floating point ordering constraints allowed the LLVM backend to recognize the math operations and auto-vectorize the loop with a vector width of 4. The GPU was suddenly processing 4 elements simultaneously instead of 1, resulting in an instant 2x throughput increase, all while maintaining strict compile time safety.
Which brings us to the ultimate synthesis. Looking at the native compiler integration, the explicit memory control interfaces, and the benchmark results, what is the core takeaway for the AI researcher listening to this?
The takeaway is that the era of sacrificing memory safety to achieve hardware-level performance is effectively ending. We no longer have to choose between execution efficiency and memory safety in high-performance computing. By linking Rust Relica directly to the LLVM offload infrastructure, developers finally have a unified, vendor-agnostic toolchain. You can write mathematically verified, deeply safe GPU code that runs identically across AMD and NVIDIA architectures, matching the execution speeds of highly unsafe C++ wide, while completely eliminating the fear of silent memory corruption. It profoundly lowers the barrier to entry for building reliable, high-performance AI infrastructure.
It really is a paradigm shift. And I want to leave you with a provocative thought to mull over. The paper briefly mentions future support for multi-device environments. If this type-driven safety model can effectively orchestrate host-to-device memory transfers with near-zero overhead, deriving its movement semantics directly from Rust's mutability rules, what happens when we scale this to massive multi-GPU clusters? Could Rust's borrow checker eventually govern memory safety and data movement across an entire supercomputer's network fabric, fundamentally changing how we write distributed AI training algorithms? Imagine a future where the compiler natively understands distributed AI training algorithms, automatically preventing race conditions and optimizing data movement across thousands of cluster GPUs by default. It could fundamentally rewrite how we approach distributed computing. Thank you for tuning in to this highly technical breakdown, and we will see you next time on AI Paper Slop.